So hello all. So this is this lecture I'm recording on mainly thermodynamic relations. Okay, you can go through it, and I think that lecture should be uh, easily understandable. But if you have any confusion, we will anyway meet on Wednesday's class next week, so you can clarify your doubt. This will save our time. Okay, so let's start with thermodynamic relations. Thermodynamic relations. So before we move, one relation is very important for us, and let's start with that. See, we know from first law that dou Q is equal to du plus dou W. Okay. Now, if we conduct the process reversibly, we know that we can write dou Q reversible is du plus delta W reversible. And I know from second law that dou Q reversible I can write TdS is equal to du plus PdV. Okay, so it simply means that, let's say, if you are going from 1 to 2, you can go irreversibly also, let's say. But if I want to know the properties, okay, or change in properties, then I have to go through a reversible path. And so I can always go from 1 to 2 through a reversible path. And if you see in this equation, okay, so this T is the instantaneous temperature because you are passing the heat reversibly. So I have chosen the reversible path. Okay. Now what this equation gives us? Otherwise, this du, ds, and dv is same while going from 1 to 2, either irreversibly or reversibly. Now what we can get from here? If we go reversibly, okay. Let's say if you go at constant volume, let's see what we'll get. So when you are saying constant volume, then in this relation, this term will go. And then what we'll get? We'll get this. We'll write this in this fashion. Dou S by dou U. Write it properly. Dou S by dou U, right? And what we have kept constant? Volume. At constant volume, okay, that will equal to 1 by T, or we should say T equal to del U by del S at constant V. So that is a very important relation which is valid throughout. So this is the temperature expression in terms of U and S. Why in terms of U and S? For that, you have to visit my extra lecture on thermodynamic postulates, which says that S is a function of U, V, and various number of moles of is the number of various species N1, N2, and so on. For closed system, we have no change in N. Okay, you can have multi-component system. Okay, so T is defined as del U by del S as constant V. Okay, that's why we are trying to define T in terms of this. Also gives us U is also function of S, V, N, and so on. These two comes from thermodynamic postulate. Okay. Anyway, if you want to skip this postulate, that's fine. But remember this through this fundamental things, first law and second law, which we have already learned. We got this expression of T. Okay, fine. What else we can get from here? So now what we'll do in the same expression, let's go to next page. TdS is equal to, we have, of course, process is reversible. TdS is equal to du plus p dv. Now you do one thing. You say at constant s, if process takes place at constant s, what will happen? Okay. So in that case, if you do the from 1 to 2 at constant s, then what will happen? Probably then s will not change, other things will change. Okay. So then what we can say, this term gone at constant s, this term gone, and then we can write du equals to minus p dv at constant s, which you can write in terms of partial derivatives at constant s. This is valid. You can write dou u by dou v at constant s is equal to minus p. These two relations are very important for thermodynamic potentials. So I am just marking it here, which we are going to use frequently. Not in my part, in other module also, next module also. T is del u by del s at constant p, and pressure is del u by del v at constant s with a minus sign, which signifies that pressure is indeed compressive in nature. Okay. What next? Now we will try to express various properties. Let's say S, H. We will soon see this. So this is entropy, is enthalpy. Then Gibbs free energy, and then Helmholtz free energy. Okay. If you write capital notations, is S, H, G, A. This is specific property, unit mass. This is extensive property. Okay, of the same thing. So let's say our first, okay, before we go, so from where we will start. Let's say we first start with S as a function of T and P. Okay, we'll keep everything in terms of these small variables, or you can keep it in capital values, so doesn't matter. So S as a function of T and P, we have always calculus which will help us. So if S is a function of T and P, using calculus you can always write. So using differential calculus, you can always write ds is going to be dou s by dou t at constant p dt plus dou s by, then s is function of t and s is also function of p, dou p at constant t dp. This you have to understand. This will be the starting point for all such kind of relation which you are going to establish. So in general, you can say that if let's say z is function of x and y, then you can always write dz is equal to dou z by dou x constant y dx plus dou z by dou y constant x dy. Remember this. Okay. Now, if we'll go through the assignments, and I have sent the solution also for that particular problem, that if let's say you write some change dz is equal to m dx plus n dy, and if x and y are intensive variable, okay, then dz will be exact. First of all, what is exact differential? That also I have written there. Exact differential means does not depend on path, only depend on states. So if this z has to be state variable, or dz, in order to having dz exact differential, this criteria must get satisfied. Del m, I have for proof you can see that assignment solution. In one of the assignment it is given dou m by dou y at constant x should be equal to dou n by dou x at constant y. So this also we are going to use a lot, and that will be the genesis of Maxwell relations. Okay, that will be the genesis of Maxwell relations. So let's apply it here in this ds. We know S is a state property. S is a state property, which means ds is a exact differential. It does not depend on path. If ds is exact differential, then if you say this is m and this is n, then what is true? Dou m by dou m by this is going to be dou m by dou t, dou m by dou p. Okay, dou m by dou p at constant t should be equal to dou n by dou t at constant p, and that you can check, that will get satisfied. Okay, that is point number one. What else we have? So as we said that we are interested in Maxwell relation, so let's see how it will lead to Maxwell relation. This you can check that this thing is satisfied here. What you will get is dou square s dou p dou t, and on right hand side also del square s dou t dou p. Now let's move to Maxwell relation. What we said, ds is s as a function of t and p, remember. So ds is dou s by dou u at constant p, okay, into dou s by dou t at constant p dt plus dou s by dou p at constant t dp. Fine. Now one relation we always have, that relation is du is equal to, if you remember, tds minus pdv. That we always have. We have just seen this is nothing but combined statement of first and second law. The moment you write pdv, it means process is reversible, so you can write dq as tds. Okay. Now let's see what this will give us, this relation, and then we'll come to this. So u is a state function, right? U is a state function. So du is exact. If that is the case, then this is my m and this is my n. And in order to du exact, what we'll write? Dou t by dou v at, so this is m, right? So dou t by dou v at constant s is equal to, here we have minus p, right? So dou of minus p by dou s at constant v. Okay, so this is our first Maxwell relation. I'll tell you how to remember it, but first let's derive it. That is Maxwell relation 1. So from where I have started? From this relation. Okay, which is nothing but first combined statement of first and second law, right? Because the moment you write pdv, it's reversible process, and you can write tds. Perfect. Now let's try to get another property, I mean another Maxwell relations. So now what we will do, we will try to write, let's say, h. Fine. So let's see if we can get something from there. So you know that dh is equal to d of u plus p, that you know. Okay. Now dh is du plus P dV plus V dP. Okay. We have combined statement of second law, because the moment you write P dV, it means process is reversible, because you are talking in terms of differential. So it means I can always write dou Q is equal to du plus P dV, and this is going to be reversible because this P dV you are using. So this I can write TdS is du plus P dV. So what I can write combining these two, du plus P dV, dH is going to equal to TdS plus this term is there V dP. Now see how this relation will help again to get another Maxwell relation. So again, H is state function, so DH is exact differential. If DH is exact differential, then this is our M and this is our N. What is true? What is going to be true? Del dou T by dou P at constant S is equal to dou V by dou S at, so dou V by dou S. So here we said dou T by dou P at constant S, and here we are going to say dou V by dou S at constant P. Okay, that is going to be true. If you have any confusion, always write in terms of N, dou M, and with respect to P at constant S, see, M with respect to P at constant S, and then N with respect to S at constant P, dou N by dou S at constant P. And what is our M? M is our T. And what is N? N is our V. Okay. So this is our second Maxwell relation. Fine. Now let's talk about another Maxwell relation. So this is called enthalpy, you know. What else? There is something called Helmholtz free energy. Let me check. I always confuse with this name. Yeah, it's Helmholtz. Fine. That is defined as A, small a, capital H for extensive property, which is U minus ds. Okay. How you can define dA? dA is going to be du minus tds minus sdt. Fine. Okay. Then we are going to take the help of our first law and second law combined. What is that statement? If you again remember, that is TdS is equal to, TdS is the heat transfer reversible, that is equal to du plus reversible work done PdV. This should help us. So from here what we'll get? We are getting du minus TdS is equal to minus PdV. Just check, du minus TdS is minus PdV. So we are going to replace it, and we are going to write dA is equal to minus PdV minus, this is here, sdt. Yeah, fine. Again, this will come to know, and you know it from here also. You see the expression of A. U is a state property, S is a state property, T is a state variable. So A is also a state variable, Helmholtz free energy. So dA is exact. If it is exact, again, we can put the criteria of exactness. So this is our M this time, and this is our N with a minus sign, of course. What we know, dou M by dou M with respect to T, dou T at constant V, and then dou N by dou V at constant T. Okay, but what is our M? You can see minus V. So minus sign out V. And what is our N? Minus S, minus out S. Minus minus sign got cancelled. So this is third Maxwell relation. Dou P by dou T at constant V is equal to dou S by dou V at constant T. Okay. Fine. And then go to another Maxwell relation. We have another property which you already know, that is Gibbs free energy. An expression of that is G is H minus Ts. Again, you can notice G is a state property because H is a state property, S is also, and T is a state variable. So dg we can write dh minus tds minus sdt. Okay. And if you remember our relation of dh, you can go back. I think a few minutes ago we have derived that dh is equal to tds plus vdp. Okay, it means dh minus tds is simply vdp. So we are just expressing one thing in another form. So dg, this can be replaced by vdp minus sdt. Again, this dg is exact, so apply the exactness criteria. But this variable, which is v, with differential with respect to time, sorry, with respect to temperature at constant p, is equal to this variable, which is minus s, so minus out s, differential with respect to p at constant t. This is another Maxwell relation. So we have all four Maxwell relation. Okay, now you can find out that every time should we start from this expression and how we'll remember this. So I've shown you the derivation that yes, we can easily derive all these four Maxwell relation. How to remember it? Very easy way. Remember this trick to remember it. Okay, so make always a square and always start from the left bottom corner, say it S. Always remember S goes to T, put an arrow. S goes to T and put P here, P goes to D. I used to remember it SPTV always, starting from left bottom corner, SPTV. Okay, now you see how easy to write it. Start from any point. Let's say I start from S. Okay, so since these differentials involve three variables, you will go till T. So go clockwise. Say this way, SPT. So dou S by dou P at constant T. Okay, take a break, is equal to, you have reached T, go to next variable and then move anti-clock, and then again you need three variables, so come till P, and I now write it starting from V. What will write? Dou V with respect to T at constant P. And what about signs? So here we have S, here we have P. If arrow is going away, then let me check whether minus sign or plus sign. Wait. Okay, so if arrow is going away, plus sign. If arrow coming in, minus sign. And that this we see, I am saying for numerator. Okay, so here we have S, arrow is going from S, so plus, and then here we have V, arrow is coming to P, a minus. So we'll get Maxwell relation, and you can check this is one of the Maxwell relation which we got. Dou S by dou P at constant T is equal to minus dou V by dou T at constant P. Okay, let's try other Maxwell relation again. S T P V. This time let's start from here. Okay. So we need three variables. So P to T till V. Write it. Dou P by dou T at constant V. Then what I said, take a pause, equal to, you have reached till V. Go to next variable S and then come back. S, V, you need three variables till T. Now write the same thing from S side. What we will write? Dou S, dou V at constant T. Now let's talk about sign. We have here P. Okay. So from P, arrow is going away. So plus. And then here we have S. From S also arrow is going away. So plus. So that is another Maxwell relation. You can check. So this way you can try. You can write all four Maxwell. Remember, this is just a technique. There is no physical meaning in this diagram. Just a trick to remember how we write all four Maxwell relations. So you can try others too. So the four Maxwell relations, if you'll see, are as follows. Just to summarize, dou T by dou V at constant S is equal to minus dou P by dou S at constant V. Dou T by dou P at constant S is equal to dou V by dou S at constant P. Dou P by dou T at constant V is equal to dou S by dou V at constant T. And fourth one is dou S by dou P at constant T is equal to dou V by dou T at constant P. We have these. So this is called Maxwell relation. Okay, what else we have learned? That dH is what? TdS plus VdP. You can see the proof. This also you should remember. We also learned dA is equal to minus PdV minus SDT. And we also learned dG is equal to minus SDT plus VdP. Okay, so these information we have till now. Change in these new these, so H, A, G, and of course S also, these are called thermodynamic potentials. Why potential? You can take the analogy from, you have done this current and voltage thing. So when there is a voltage difference, current flows. Basically it's a potential difference. So it means whenever there is a difference in these variables, there will be some thermodynamic process, and that's why we call it thermodynamic potentials. If you create d of h, d of a, d of g, d of s, some thermodynamic process will flow. I mean, it will take place. Okay, fine. So we have Maxwell relation, we have thermodynamic potentials. Now we will see different other thermodynamic relation. Before that, and we have expression of T and expression of P. Okay. Again, there is another assignment problem which you should see the solution, and it will help you with because we are going to use it a lot. What it says, that if you have three variables x, y, z, and if z is a function of x, y, which is equivalent to saying f of x, y, z 0, right? Because it will be some linear equation of x, some equation, not linear, some equation in x, y, z. So you can always say f of x, y, z is 0, putting bringing everything on the right hand side. Okay, say it z is function of gxy. So z minus g of xy is 0. With this I can say f of xy z 0. Whenever you have this thing, you can always write dou x. So remember in cyclic manner, dou x by dou y at constant z, x, y, z. Then we started from x. Now start from y. Dou y by dou z. Dou y by dou z constant x. Then start from z. Dou z by dou x at constant y is equal to minus 1. This is true. You can check the derivation in the assignment solution. Okay, this we are going to use a lot. What else? Dou x by dou y, let's set constant z. This you can write 1 by dou y. This is very trivial. By dou x constant z. Okay, so this we are going to use a lot. Now let's see some illustrations. Before that, we have to also define. Let's go to here itself. We have to also define beta, which is known as expansion coefficient, isothermal expansion coefficient. Okay, isothermal expansion coefficient. And as the name suggests, so when you are saying expansion, so change in volume by original volume, and then we are saying it that it should be, let me check whether it's expansion coefficient equals, sorry, let me check what it is called. Just a moment. Okay, because in compressibility we keep the temperature constant. Here we will vary the temperature. So let me check what we call this beta. I don't remember. Sorry, since here temperature will vary, it's called thermal expansion coefficient. A real gas will expand when you will increase its temperature. So not isothermal, thermal expansion coefficient. So you can see that dou v by dou v is relative change, fractional change in volume with respect to temperature, keeping the pressure constant. So this is the definition of beta. That's how I remember. Okay, because how you remember beta? So it's a fractional change in volume, where v is the instantaneous volume and dv is the change, and how it will change due to the temperature difference at constant pressure. That is our beta. Then there is something called isothermal compressibility. Since we are talking about real gases, these both terms are important. Okay. So again, since we are compressing it, it is going to be dou v, no doubt, by v. That is always there, fractional change in volume. But this time, since you are compressing, so what you need to use? Pressure. So dou p. Okay, fractional change in volume dou v by dou p at constant T. Otherwise, it will be very difficult to define. And since pressure is always compressive in nature, there is a minus sign. Okay, so this is our, and this is called kappa. So we'll see things in terms of kappa and beta. You can calculate kappa and beta for an ideal gas. Try it. Okay, great. So let's do some illustration. Okay, a few more things. What is Cp and what is Cv in general, not for ideal gas. So Cp, what we know as heat given at constant pressure reversibly. Okay, let's say constant heat given at constant pressure by this divided by change in temperature. Okay, so let's say dt. Now, if you do reversibly, you can always write dou q given at constant pressure is equal to, we can write du plus pdv. Okay, and then you know that since process is happening at constant pressure, there is no harm in adding vdp because dp is anyway 0. This is equal to 0. This will help us. Du equals to d of pv, and this is nothing but if you combine it's dh. So what we got, but remember at constant pressure. So Cp is dou h by dou t because dqp is becoming to dh constant pressure. So this also we are going to remember. Cp is dou h by dou t at constant pressure. What else we can remember? there are few more expression of Cp. Let me derive it for you. From where we should start, I'm just thinking. So for dH, what we know is, if you remember the relation dH is TdS plus VdP. Okay. Now again, you can ask that how, sir, how you remember this dH in terms of SNP and all this. I'll tell you the trick. Okay, but first let's do this and then I'll tell you the trick. So dH is TdS plus VdP, and this is our definition of Cp. Okay. So remember, this whole thermodynamic relation is completely mathematical. So just play with mathematics. We see what we'll get here. So what we want, dou H by dou T at constant P. Let's do it. So differentiate with respect to T, this equation at constant P. So dou H by dou T at constant P. Here we have T dou S by dou T at constant P plus this term at constant P is 0. So dou H by dou T at constant P is coming out to be T dou S by dou T at constant P. So T dou S by dou T at constant P. So what we have for Cp? For Cp, now we'll remember, of course, this you will remember, dou H by dou T at constant P. This is also equal to, in terms of S and T, T dou S by dou T at constant P. This also going to help a lot. Cv. Okay. So Cv, you know, heat given at constant volume by dou T. Now you know heat given constant volume, we'll write. So it's going to be equal to simply dou U. Okay. So du by, rather than saying dou U by dou T, because the process is happening at constant V. Okay. But we also know du is what? dq minus dw, reversible if we do it, tds minus pdv, right? Because this is dou q reversible, and why I'm writing reversible? T at constant v. So basically differentiate this equation with respect to T at constant v. What we will get? T dou S by dou T at constant v, right? This term will be 0. So what we get for Cv is, of course, dou U by dou T at constant v, but that is also equal to T dou S by dou T at constant. So this we are going to use in places. Fine. What else? You can ask that, sir, how you remember this du relation or dh relation. That is very easy, again through that diagram. So you remember this diagram where we said S to T, B to V. Then what you need to remember is, start from here. That you have to remember, that H, G, A, U. Now you can put any, any rhyming to remember this order H, G, A, U. Right? Like what we can do. Let me think that what you can do. Whatever, like you think that what you, I mean, I can think a lot of things that how you remember. You can H for something, G for something, A for something, E for something, make it in some bit rhyming, you'll remember HGA, and then it's very easy to retain. Let's say if you want to write DH, okay, small or capital. So H is connected with S and P, right? So write it DS DP. Again, I'm repeating. If you want to write H is connected with S and P, DS DP equal to, now S is going to T, put T here. P is going to V, put V here. What about sign? So since arrow is going from S, it's going to be plus. Since arrow is going from P, it's going to be plus. So DH is TDS plus VDP. Very easy to remember. Okay. Let's check for other. If you want to write DG, what is the G is connected with what? In T and P. So write DT and DP. Simple. Then T T is coming from S, and P is going to V, so V. And what about signs? So you see here T and P. Arrow is coming towards T, a minus sign. Arrow is going away from P, a plus sign. Okay, so dg is minus s dt plus vt. That's how I remember. Let's say I want to write dA. dA is connected with what? V and T, right? Write dV dt. Then V is coming from P and T is from S. About sign, so V and T. V arrow is coming in, minus sign. T arrow is coming in, minus sign. So for sign you have to see this differential variable. Okay, so that's how you can write D. And du also you can write, right? It's not a big deal, similar. Okay, so that's how I remember. Great. Now one illustration, and then rest of the two illustration we'll cover in the class on Wednesday. Okay, so the relation which we are going to do is simple one. TdS, prove that TdS is equal to Cp dt minus beta V TdP. Remember, these are all for real gases. You can always calculate it for ideal gas, calculating beta, Cp, all this. This is in general true for any real fluid, right? Okay. So let's prove it. So from where we will start, right? So we should start from, let's say, expression of no, rather than we can start from here. We want to express S in terms of T and P, right? So S in terms of T and P. That's what I can see right now. So what I will do, I will write ds as dou S by dou T at constant P dt plus dou S by dou P from maths, from calculus. Dou S by dou P at constant T dP. Okay. Now you can see you want here Cp. So let's see the definition of Cp. You can check. You already derived expression for Cp. Cp is T dou S by, I don't remember. Let's check it. So Cp is dou S by dou T at constant P. Dou S by dou T at constant P. And Cv is, just remember, T dou S by dou T at constant V. Anyway. So ds is equal to this. You can simply see this one from here, Cp by T. So this is fine, Cp by T dt. Okay, plus what about this term, dou S by dou P at constant T. Okay, now probably Maxwell relation will help us. So if you want to write Maxwell relation, what we'll do quickly, you can remember this diagram, S T P V, and let's see whether Maxwell relation help us or not. So you want something for this, write down from here. So SPT, right? So we'll go this way, dou S by dou P at constant T, and take a break, move one variable ahead and come here, P, three variables is equal to dou, now start from V, of course, dou V by dou T at constant V. And what about sign? So you see S arrow is going away, plus sign. You see V arrow is coming in, a minus sign. So dou S by dou P at constant P, using Maxwell relation, I can replace it with this. So let's replace it. I am replacing it using Maxwell relation. Okay, so this will be minus sign dou V by dou T. I guess there is no mistake in sign. I think yes, but we'll see if there is a mistake. So dou V by dou T at constant P dP. Okay, so we are up to this point. Now let's see the definition of beta. As I told you, how you should remember beta: fractional change in volume, and then because we need beta here, and then temperature you have to change at constant P. Okay, so what we will get from here, you see, dou v by dou t at constant p will get beta into v. So this expression we are getting as beta into v using this dp, and there is a minus sign. Cp by t dt is equal to ds, right? But you need tds, so you have to multiply this whole equation by t, and then you will get what we want to prove, which is tds is equal to cp dt minus beta v t dp. Yeah, perfect. Okay, so that's how. Let's take another example. One more example. Let's say you want to express s. You want to express s as a function of t and v, basically in terms of measurable properties. So you have to prove. Let's say someone asks you to prove that t ds is equal to cv dt plus t beta kappa dv. So basically what we are doing here, you can see that we are trying to express these thermodynamic potential in terms of state variable, which are what? V, T and P. Okay. What is the target? You think that we are not doing things randomly. What we are trying to do, we are trying to express various thermodynamic potentials like H, S, A, G in terms of state variable, which is PVT, and we need other things also like Cp, Cv, and we need this. Since there is expansion and compression, we need this beta and kappa also. That's what we are trying to do. Okay. So that's why you see this relation ds in terms of state variables and these things. So let's do it. So again, what is our target? S as a function of t and v. S as a function of t and v. So using calculus, I can write my ds is dou s by dou t at constant v dt plus dou s by dou v at constant t dv. Okay, fine. Now this you can see directly here. If we go to the definition of cv, this will be cv by t. You can check, this is cv by t. We have derived it. Okay, so I will be quick here, you can check it. Plus now we have to talk about this term, del s by del v at constant t dv. One way is that you play with beta and kappa, you should reach here. That is also possible. Okay, and if someone want a bit twisted way, then also we can do it. Just let me see how I'll reach here. So this is fine, cv dt by t, and now we have del s by del v at constant t. So let's see Maxwell relation help us or not. For Maxwell relation, what we have? S T P V. Yes. So there is a scope. So you want SVT. So you want something this way. So you have to start from here, right? According to our rule. And again, as I told you, this is just a technique. Ultimately, these the relations we have derived. So what this will give us? If we start from P, dou P by dou T. You see, dou P by dou T at constant V. Then take a pause. Come here to next variable S. Then move back. Dou S by dou V at constant T. What about sign? P arrow is going away, right? So plus sign, no problem. S arrow is going away, plus sign. So we can replace dou S by dou V at constant T with this using Maxwell relation. So what we have using Maxwell relation, ds is equal to cv t dt plus dou p by dou t using Maxwell relation, dou p by dou t at constant v dv. Okay, fine. Up to this point it's fine. Now let's see beta and kappa help us or not. You can see here clearly, you want to derive this and you have this thing. You can clearly see we have P change in pressure, and we have change in temperature. Okay. Now let's go to beta. Beta, what we have is dou V by V, fractional change, dou T at constant P. What is kappa? For kappa we have dou V by V with a minus sign, dou P at constant T. And what we have here is dou P by dou T at constant V. Let's see, we can correlate dou P by dou T at constant V. Okay. So if you take this, let's say cyclic relation help us or not. Maxwell we already used. Let's go to cyclic. So I write it in this lesson, PTV. Use a cyclic relation. We know that equation of state says as f of PTV is 0. There will be some equation of state. Okay, we are not using it randomly. We know there is some equation of state with this PTV. So what we can write? Dou P by dou T at constant V. Then start from T, dou T by dou V at constant P. Then start from V, dou V by dou P at constant T is equal to minus 1. Right? From that cyclic relation. We want this. This is what we are looking for. And this, if you'll see carefully here, this is beta V. No, what is this? 1 by B. So this is, yeah, this is 1 by dou T by dou V at constant P is nothing but 1 by beta V. Okay. So this is nothing but 1 by beta V. And you see this dou V by dou P at constant T here. This is dou V by dou P is minus kappa V. Minus kappa V. And then here we have this term as it is. V get cancelled. So what we got? Dou P by dou T, what we are getting? Kappa by beta. Okay. Now let's go to our another. So we found this term kappa by beta. So then you can go back. This we have proved this is nothing but kappa by so what we want, dou P by dou T at constant V, right? So what we got, dou P by dou T is to beta by, so not kappa by beta, beta by kappa, right? Because these are in product. So sorry, what we'll get, dou P by dou T constant V is beta will go that side, so beta by kappa. Just replace it here. So we'll replace this term by beta by kappa, and then we'll get your desired relation. ds is equal to, well, right now what we have, just check, ds is equal to cv dt by t, and then beta by kappa dv plus beta by kappa dv. So if we multiply with t, we get t ds is equal to cv dt plus beta kappa t dv. That's how you can get it. Okay. So similarly, you can try. I'm giving you as a jump or home assignment. That try it for, let's say if you want to express H as a function of temperature and pressure, and you have to prove that we can express H as a function of temperature as this: dH is equal to Cp dt plus V minus T beta. No, okay, so this is what T minus beta V. Basically, you can take V common, dV. Okay, that you are supposed to derive. Again, you can see the motivation. You want H in terms of what? State variables, that is T and P, and of course V also, and then other things, beta, kappa, whatever it is, Cp, Cv. So as I said, although I am saying it home assignment, let me give you some hint. You again start with H. You want to H as a function of T and P. So you should always write dH using calculus. Take the help of calculus. you can write dH is dou H by dou T at constant P dt plus dou H by dou P at constant T dP. Fine. Right. Now what we should do? So dou H by dou P at constant T. Now, do we have any help for dou H by dou P at constant P? That kind of CP was CP was dou H by S. That we know. Okay, that we have already derived. While deriving CP in terms of S and T, we already see dou H by dou T at constant P. So this is fine. CP is directly there, no problem. We have to think about this dou H by dou P at constant T. So how we will reach there? If you remember, so this we know at CP, no issue, right? This is sorted out. CP, we have to think about this. So for this DHDP, we have to think some thing where we can express H in terms of P. If you remember this diagram, you know, S, T, P, P. Since it's difficult to derive every time, you can always use this trick. H, so what you want to write? DH. So you can write DH as, you can always write DH. What is H is connected to S and T. So no, this is not going to help us. We want in terms of P, right? So rather than going here, oh sorry, I have drawn this diagram wrongly. So S goes to T and P goes to V. Now I can write. So using this, what we can write? DH is equal to, now you can see it will be DS and dP because H is connected to S and P, and then S is going to T and P is going to V. What about sign? You see S going away, so plus sign, P going away, plus sign. Okay, so DH is TDS plus VDP. Now you can see what we want, del H by del P at constant T. You see here, dou H by dou P at constant. So take derivative both sides at constant P. Let's see what we'll get. Dou H by dou P. Sorry, at constant T, not P, at constant T. Dou H by dou P at constant T is T dou S by dou P at constant T. And then this will get plus, so what we are getting, dou H by dou P at constant T, yeah, and we are taking derivative with respect to pressure, right? So this will be simply V, dou P by dou P is 1, right? Dou H by dou P at constant T is T dou S by dou P at constant T plus V dou P by dou P is V. So this we have. So what I'm going to do, this will be replaced by Cp and this will be replaced by this. So let's do it. DH is what? Cp dt plus, we are replacing this by this. So this will be plus T dou S by dou P at constant T plus V. And then what we have here, which is differential into dP. So we have replaced this by this into dP. Okay. So see what we have created. DH is equal to Cp dt plus VdP is already created. That's a big relief. VdP we have. Now we are remaining with this VdP, right? What we have, T dou S by dou P at constant T dP. Fine. And now what we should do, maybe we can use Maxwell relation here. Let's see, in order to do something with this. So again, this will help us. S going to T, P going to V dou S by dou P. We are starting from here. Dou S by dou P at constant T. Then take a break, one ahead, come back, to P. What we have? Dou V by dou T at constant P. What about signs? So S going away, plus sign, V coming in, minus sign. So we can replace dou S by dou T at constant T with minus dou V by dou T at constant P. Let's do it. So we are replacing this with, using Maxwell relation, we are replacing it with so minus dou V by dou T at constant P. Okay, this minus you can put here. And now what you can do, that let's say put one V here and one V here, that I can do V multiplication, V division, and this I certainly know fractional change in volume by temperature is beta, this quantity. So dH is dP dt plus V dP minus T is here, then this whole term is beta. We multiplied with one V also to manage this V dP. So we have proved already dH is Cp dt plus V minus T beta V dP. Okay, so that's how you can find different relation. So go through this, practice this, and this will help you. So now we are only remaining with feasibility criteria, which is very easy. I have put it as an assignment also. I'll upload the solution, and then when we will meet on Wednesday, a brief discussion on this. If anyone has any confusion, maybe I can solve one more problem, and then we'll go to question of state. And combining with this, what I'm sending you through this video and the question of state, which we'll cover in the next class. There will be a short evaluation test on Friday's class by Professor Gargidas, so that you can smoothly make a transition to another module. And we will add that part to the total marks. It will not contain too much contribution to the total marks, but yes, that will be an evaluation test. Thank you.